As I mentioned, we are going to move into chapter 3 this evening. We're going to cover 3 sections, so 3, 1, 2, and 3. In chapter 3, we're going to start looking at applications of differentiation. And so this first section, so in general, chapter 3 is going to explore many applications of differentiation. We will learn to find the maximum and minimum values of functions. And this will then allow us to solve many types of problems in which we need to optimize a value in a real world situation. But in this section in particular, section 1, we will use what we're going to learn as the first derivative to classify maximum and minimum values, and then use that information to help us sketch graphs. Okay, and so everything that we do in this section, or in this chapter actually, will continuously build so that at the end of the chapter, we'll be able to graph some of the more complex graphs based on the techniques that we kind of learn and pick up along the way in each of these sections. So this first one, this first section, we're going to use the first derivatives to help us determine maximum and minimum values in our graph. Okay. And so I've posted here a couple of definitions for you. Nothing out of the norm, right? If a graph or a function is increasing over a specific interval, we can expect that that our A value is, if it's to the right of our B value, so then we can expect that outputs of A will also be less than the outputs of B if our graph is increasing. And so that's kind of to this graph here on the left, right? So if my A is smaller than my B, right? My X1 is smaller than my X2, then the output of A is also less than the output of B, then that means my graph is increasing. Okay. The same is true if we flip it, right? So now if we say if our A is still less than B, but our output of A is greater than B, right? So we still have A and B as our X1 and X2 values. But now, if my A value is greater than my B value output, then that means that my graph or the slope is negative or decreasing. Okay. So that's all those definitions are telling us. I put it here in the PowerPoint or the PDF that you guys will be able to download so that you don't have to go search it out in the textbook. But if you wanted to see that in your textbook, it's on page 265. All right, question. All right. So we need to learn a couple of theorems to help us before we get started with graphing. The first theorem basically tells us that if we have an open interval, if we look at the first derivative, right? If the first derivative is greater than 0 for all of the x's on that interval, then our function f is increasing on that interval. And if our first derivative is less than 0 on that interval, then our function is decreasing on that interval. Okay. Introducing a term, critical value. So our critical value is really a point or a number on it has to be in the domain for which our tangent line is horizontal. Okay. And so when we look at this and we look at our critical value, right? So if we take the derivative and we evaluate it at what we believe is a critical value, it needs, if it equals 0, right? Then we could have a critical value. But if the derivative doesn't exist, then we might not have a critical value at that point. Okay. So if C, this is that it could be whatever value that is, right, is a critical value, then we have to be able to evaluate our function at that value in order for it to be a critical point. Okay. Another theorem, this theorem number 2 in the chapter. And so basically this one is saying if we have a function and it has a relative extreme value on an open interval, then C is a critical value and the derivative evaluated at C is going to be either 0 or it doesn't exist. And then that leads us into our third theorem, where we are going to use the first derivative test for relative extreme. Okay, so what we do here is when we have a continuous function and it has exactly one critical value on that open interval, then we look at it and we need to determine if the function has a relative minimum, then our first derivative is less than 0 from A to C, and our first derivative is positive or greater than 0 from C to B, right? So if you think about that, if we had, remember we had A is here and B is here, and we're looking at some critical value on that interval from A to B. So what this is saying is if my first derivative is less than 0 on the first interval and greater than 0 on that second interval, then my function is decreasing to the left of C and it's increasing to the right of C. Okay. The flip is true as well, right? So if I am greater than 0 on this interval and less than 0 on this interval, then I'm going to be increasing on the left and decreasing on the right. And if for a function that has no max or minimum, then the sign stays the same. And so it would just be a straight line in the positive or a straight line in the negative, meaning that there's no change, that the sign is the same. So either they're both greater than 0 or both less than 0, but they don't switch between them. And therefore I don't have a minimum, nor do I have a maximum. Okay, questions? And we'll see all of this in example. Okay, so this right here, this is coming, let me flip in the book and tell you what page that's on. This is on page 268 of your textbook. Okay, and so this is basically what I just gave you in all of those theorems. This is kind of laying it out graphically. And so we can look at it, right? So what this is saying is I have a relative minimum if I am decreasing from A to C and increasing from C to B. You can see that that means I have a minimum point on my graph, right? And so you can see here, this box here tells me that my first derivative is negative, and my first derivative on that interval from A to C is negative. My first derivative from C to B is positive, and so that's how we can keep this in mind, right? So if we move to the next one and we want to look at a relative maximum, if I'm increasing and then decreasing, you will see I have that maximum point, and that gives me the relative maximum. And then the other case was, you see I'm negative and I'm negative again, so I have no maximum or minimum. We'll learn that this right here is actually an inflection point, okay? And then if I'm going positive and positive, you will see again, I don't have a maximum or a minimum, but I'll have an inflection point, okay? Questions? Now I erase these notes out so that you guys don't have that when you go to reference this. Okay, questions? All right, so let's look at some examples then. So this first one, this is on page 276 in your textbook. It is number 6. I'm going to flip there real quick so I could read the instructions. So this one says that it wants us to draw a graph to match the description that's given. Okay. So the description that's given here is that our function is decreasing from negative infinity to -3. So here is -1, 2, here's -3. So right about here, I drew this line. I'll erase it when we're done doing our graph. But what this is telling me is that my graph is decreasing in this direction and it's increasing in this direction, right? And so ultimately, we can come in here and say it could be something like this, right? It could be a graph like this, like all kinds of things, right? But the point is, in what we were given is we know that from here to here, our graph must be decreasing. And from that blue line at where x is equal to -3 to the right, our graph must be increasing. Okay. So if you were asked to do something like this on homework or exam or some homework in the My Math Lab, it'll just give you like 4 graphs to choose from and ask you to pick. If I were to give you something like this on the exam, I wouldn't care if you drew something like this, right? So long as it's decreasing on the left of the blue line and increasing on the right of the blue. Okay. Any questions? All right. So this next part, this is number 12. Same instructions. This one says that our function has a positive derivative over the interval negative infinity to -2. So here's -2. So this is, so this is that. So that's one interval. And it's also from 4, 1, 2, 3, here's 4 to 7. So that's 5, 6, 7. So on this interval, it is also positive. So remember, positive derivative means we're increasing, and a negative derivative means that we're decreasing. And so from -2 to +4, our graph is decreasing. And from 7 to infinity, our graph is decreasing. So I draw those arrows down at the bottom to kind of help guide me to, it doesn't give me any other guidance at all, but I do know that I'm going to have a maximum here because I'm going from increasing to decreasing, right? So this right here tells me that I'm going to have a maximum, right? And this one here, where I'm going from increasing to decreasing, means I'm going to have a maximum at this point here as well. So I can put a maximum anywhere. Let's put this one right here. So those are my 2 maximums. And then when I'm shifting from minimum, from decreasing to increasing, then somewhere on this line means I'm going to have a minimum, right? So I could draw in my graph here then, could be anything like, oops, didn't mean to do that. Right? So the graph could look anything like this. So I have a maximum here and here to my, oh, sorry. Let's try that one more time. So I have a maximum point to my graph at the 2 blue dots, and I have a minimum point to my graph at the 1 green dot. Okay. But again, we could have drew those in many different ways, right? I could have been up here, down here, something like this. Or we'll leave that one. It could have been something like this, right? So it doesn't particularly matter as long as you're adhering to, I have a maximum and I have a minimum on those specific points. Okay? Question. All right, so let's look at a problem where we have our function equals x squared minus 6x plus 1. And so the instructions for this part is they A, want us to find the critical values, and B, find relative extrema. Okay, so first let's look at our critical values. Okay, so for our critical values, what we need to do is let's look at our derivative. So first, our f prime is going to equal 2x minus 6, right? All I did was take the derivative of our original function. That's something we all should be very familiar and comfortable with at this point. Okay, now our derivative does exist for all real numbers. Okay, so our f prime can be set to 0. Okay, so now we can say 0 is equal to 2x minus 6 and solve for that. So that gives me 2x equals 6, so x is equal to 3. So there is one critical value, and that is 3. So we have 2 intervals. Okay, so we have one critical value. I'm trying to write it all out here for you guys for the first one, so you have something to reference back to when you do your homework. So we have one critical value. So I'm actually going to say our only critical value is 3. Sometimes if this had been like an x squared equals 9, then we would have taken the square root and we would have gotten x equals positive 3, x equals negative 3. So we would have had 2 critical values. This case, we only have one critical value. Okay. Since we only have one critical value, we have 2 intervals. So think about that critical value. So we'll say interval A is going to be from negative infinity to the critical value. And our second will be from the critical value to positive infinity. Had we had positive 3 and negative 3, it would have been 3 intervals because it would have been negative infinity to negative 3, negative 3 to positive 3, and positive 3 to infinity, right? We have to cover the whole entire number line, but every time you have a critical value, we must have a break in the graph. okay, or in the interval, okay? So now we will use a test value in each of those intervals to determine the sign of the derivative. This is very similar to if you think back to algebra days when we're trying to solve inequalities and building out a table. This is very similar to that. All right, so we have our interval. And so the interval is that negative infinity to 3, 3 to positive infinity. Okay, we need a test value. We want to know what is the sign of our derivative. And then let's discuss the result. Okay. So we want to pick a value in the interval. Notice there's parentheses on both the negative infinity and the positive 3. So we cannot choose those values because they are not part of it, right? That's what the parentheses tell us. They're not included. It just gets really close to them. I would say we're going to choose x equal to 0 in this first interval because I always want to choose the one that makes my computations the easiest. And so having a 0 will definitely make our computation a lot easier. And then on this one, we'll choose the smallest value we can, which is 4. Okay. So when I substitute x equals 0 into my derivative, remember my derivative was 2x minus 6, right? So f prime evaluated at 0, okay, is going to give me 2 times 0 minus 6, which is equal to negative 6, which is less than 0, right? I'm going to write that on the next line. So this equals negative 6, which is less than 0. So because my derivative is negative or less than 0, my result is I am decreasing. Okay, so my graph is decreasing on the interval negative infinity to 3. Okay, so for my second interval here, I'm looking at the derivative evaluated at 4. So that is 2 times 4 minus 6. That is 8 minus 6. So that is a positive 2, which is greater than 0. So my derivative is positive there. Therefore, my graph is increasing. Okay. So my function is decreasing on the interval negative infinity to 3, and it's increasing on the interval 3 to infinity. Okay. The change from decreasing to increasing indicates a relative minimum occurs at that x equal to 3. Okay. So, and we can see that if we kind of were to connect these dots right here like that, right? We see this and we can see that that is a minimum. Okay. And so what we want to do now is substitute that 3 back into our original value or our original equation to see what that value is, right? So we're going to sub our critical value. So we'll sub x equal to 3 into the original equation. Okay. And so we get f of 3 is equal to 3 squared minus 6 times 3 plus 1 equals negative 8. So we have a relative minimum at that point 3, -8. Okay? Questions. And that was part B, was to determine the relative minimum. Or relative extrema, it could have been a minimum or a maximum. Okay? Question.
Professor,
Yes.
so are you gonna want us to do all this in a test?
Yes. And so, and it actually will be a lot more steps. And so the problems, you'll have less problems on the next exam. And they'll just be worth more points. So, but yes. I would recommend, I'm not going to require that you do it in this table tabular form, but I promise you it'll help you keep your work straight. Okay?
Okay, thank you.
Uh-huh. Any other questions? Okay, let's look at another example. So for this problem, this number 34, it is saying in this part, it wants us to find the relative extrema of the function, and it wants us to list each of them along with the x value at which it occurs, and then identify intervals over which the function is increasing and over which it's decreasing. And then we're going to sketch the graph. Okay. So as I mentioned, we're going to learn a lot of little steps, and we're going to put them all together and over the course of this chapter, and be able to graph more complex graphs, right? Because typically, if I ask you to graph this, this is not something that we really are. I mean, we could plug in a 1, plug in a 2, get our x and our y values out. But where do we even know? Do we even know if 1 and 2 are enough to cover the full shape of the graph and that sort of stuff? No, not really. And so that's why we can use calculus to help us understand better what our left and right limits are, so that we can capture the graph in a fuller picture. Okay, so when we are given a problem like this, the first thing we want to do is find our critical values, right? So I'll write here, we first find critical values. You could call them critical points, critical values. I think the textbook calls critical point. Okay. So the first thing you want to do when you want to find the critical point is, let's first find our derivative, right? So our derivative of this, the derivative of 5 is 0. The derivative of negative x is -1. Derivative of negative x squared is -2x. Okay. So our derivative exists for all real numbers. So we can set it equal to 0, right? So if this did not exist for all, let's say we ended up with 5 over x as my derivative, then my derivative does not exist for all real values, because I can't plug a 0 in here because I would get it as undefined. So therefore I wouldn't have a critical value. Okay. But in this case, especially when we have linear things, they're always they always exist across all real numbers, and that is the case here as well. Okay, so we can set our derivative equal to 0. So that would be 0 equals -1 minus 2x. So 2x is equal to -1. And x is equal to -1/2. So this is my critical point. And I only have one of them, as like I did with the previous example. So if I build out my table and I want to look at what are my intervals, I only have one critical point. I know it has to go from negative infinity to my critical point, and then my critical point to positive infinity. Okay. I'm going to have a test value. I'm going to do my first derivative and what is the result of that. Okay. So on my first interval here, I can pick a test value of x equal to -1. My second interval, I will pick that x value equal to 0 because I always try to choose 0. All right. So when I plug my derivative evaluated at -1, that gives me -1 minus 2 times -1. So that will give me a +1, which is greater than 0. So that means I am increasing. For the second interval, my derivative evaluated at 0. That gives me -1 minus 2 times 0. So that is -1, which is less than 0. So my graph is decreasing. Very similar, right? So that tells me here, if I look at it like that, that I have this, it indicates that I have a relative maximum. Okay. So again, I can evaluate my original function at this critical point. So my original function was, we're going to evaluate our original function at this -1/2. So that is 5 minus -1/2 minus -1/2 squared. So this gives me 5 plus 1/2 minus 1/4, which is 21/4. Okay. So I have this relative maximum at the point at this point, -1/2 21/4. Okay. So that is the first, that is exactly what we did on the previous problem. This time, though, this asked us to also include a graph. So I'll just do that over here. Okay. So one of the things that we can do is, let me just scoot it here, build a table to help us get some more defined. We'll put f of x here instead of y, same difference though. And let's look, we know that our critical point is this -1/2. And that occurs, we know, at 21/4. So let's get a couple of points on either side of it. So we could look at -1, -1, -2, -3. We can also look at 0, 1, and 2. Okay, so when we plug those into our original equation, we end up with -1, 3, 5, 5, 3, -1. Okay, so we'll plot those points. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so we have -3, -1. We have -2, 3. We have -1, 5. We have 0, and this is a little over 5. So we'll put that about right here. Okay. Then we have, oops, that 1/2, negative 1/2, about right here. Now we have 0, 5. So that's right here. We have 1, 3, and we have 2, negative 1. So that is roughly what that graph would look like. And you could put that graph, you could put 5 minus x squared into your calculator, and it will give you a graph somewhat similar to this one. Okay. On your exam, I would just ask, if you don't use graph paper, just sketch it out just how I did here. If you put the tick marks, then I can count the tick marks. If you don't put tick marks and you just want to come up, you have this and you put this here, you could put 5 and put a dot there. I'll understand what you're talking about. But you just need to make sure and get in the habit of labeling your graph, so that whoever's viewing it can understand what you're talking about. Okay. Question. All right. The last example from this section is looking at temperature during illness. And so the temperature of a person during the illness, this is an intestinal illness, is given by the equation here. And we want to find the relative extrema and sketch the graph of this function. Okay. So the first thing we need to do is the derivative. Okay. So the derivative is going to equal negative 0.2t plus 1.2. Okay. And this is right here telling us that we're on this interval from 0 to 12. So we're not actually looking from negative infinity to positive infinity. We are restricted to 0, time equals 0, all the way out to time equal 12, where time is in days. So from 0 days to 12 days. Okay. Our derivative exists for all real numbers, so we can set our derivative equal to 0 and find a critical value. Okay. So we can take negative 0.2t plus 1.2, set that equal to 0. And we would get negative 0.2t equals negative 1.2. Thus, t is equal to 6, and this is my critical value. Okay. So our interval will be divided up from 0 to 6 and 6 to 12 instead of infinity. Okay, so we have our interval. And so it will go from 0. Notice I have a bracket on 0 to 6. The critical value does not get a bracket, it gets parentheses. And then from 6 to 12 with the bracket. And again, that is because we have equality in the time that we were given. Okay. All right. So our test value can be 0 for the first interval. So we can let we can let t equal 0 because that is inclusive. 0 is included. For this one, though, we'd want t equal to 7 because it is not included. The 6 is not included. So what is our f prime, right? So our function evaluated at 0 is going to be equal to 1.2, right? So that would be 0.2 times 0 plus 1.2. So that's 1.2, which is greater than 0. So we are increasing. Okay. F prime evaluated at 7, that is going to give me a negative 0.2, which is negative, and therefore we are decreasing. Okay. And so for this one, I'm going from increasing to decreasing. So I end up with a max, a relative max at t equal to 6. So we can plug that back into our original equation. So t evaluated at 6 is going to give me negative 0.1 times 6 squared plus 1.2 times 6 plus that 98.6. And you will see that that is 102.2. So I have this relative maximum at that point 6, 102.2. So what that's telling me is on the 6th day, I have my maximum amount of fever, which is 102.2 degrees when I have this intestinal illness. Okay. So the last thing we want to do is sketch out that graph. So let's go ahead and sketch some X and Y values. Actually, it's T and F of T values. So we could do times 0, 3. I'm going to do 5 just to give a little bit of granularity. 6, 8, and 12. So we get a little bit of everything in here. So when I plug 0 into my original, I get 98.6 degrees. Plugging in 3, I get 101.3. 5 gives me 102.1. 6, we already know is 102.2. We got that from evaluating at our critical value. 8 is 101.8, and 12, we're back down to 98.6. Okay, so we can plot these points. If I let this be 99 degrees, this is 100, 101, 102, and 103. Then at t equal to 0, I am at 98.6 degrees. At 3, at t equal to 3, so here's 1, 2, 3. I actually, because we're going to 12, let's do 2, 4, 6, 8, 10, 12. So at 3, I'm going to be at 101. So that's 101.3. Let's go a little above the 100 line. At 5, I'm at 102.1. Then at 6, we're the 102.2. So we're really close, just slightly higher. Now we're going to start our drop back down, right? We've reached the peak of our illness, and now we're going to start coming back down. If we look at 8, we're at 101.2. So we're not quite up at 102. And finally, at 12, we'll be back at 98.6, somewhere around right here. So you can see that the illness peaks out right here and then comes back down. Okay. Question. All right. So let's go ahead and move into 3.2. And so in this section, what we have is we're going to start looking at the second derivative test, right? So what we just did was what was the first derivative test. Now we're going to move in and look at the second derivative test. And this is going to help us to classify maximum and minimum values as well. And it will also help us to show whether a graph is concave up or concave down. Okay. And so I put the definition here for you. If our function is concave up, if the first derivative is increasing, and our function is concave down if our first derivative is decreasing over the specific interval. Okay. And so now when we take and look at the test for concave, we're looking at our second derivative now. And so if our second derivative is greater than 0 over our interval, then we're going to be concave up. And if our second derivative is negative over that interval, we will be concave down. Okay. And so a little bit on our second derivative test, we have that theorem there that basically tells us that if we have this critical value and we have a relative minimum, if our second derivative is greater than 0, we have a relative maximum if our second derivative is less than 0. Okay. And if our second derivative is equal to 0, then we can use our first derivative test to determine whether we have an extrema or not. Okay. As I mentioned a little earlier, when we were looking at the chart with the table, I talked about an inflection point. And so that is introduced in this section in theorem 6. And so you'll have an inflection point if you have a case where our second derivative evaluated at a specific point P here in this graph is equal to 0. Okay. And so in this case, you could see I'm clearly shifting from concave down to concave up. So that's an inflection point. Okay. But for this one, there's not a clear shift from up to down, right? This is like it's coming sideways. It's not coming from it's not coming like this, right? It's more coming like flat line. And so I would not, my second derivative would not exist at that point of the P. Okay. But it is, again, here you could see that I have a clear defining from where I'm concave up versus concave down. And that does give me that inflection point. Okay. So this is really just for you all to not have to search it out in the textbook. If you want to look at it in the textbook, it is on page 286. And this is really just the strategy for how we're going to graph these functions. Okay. And so first we want to graph we want to determine the derivative and the domain, the derivatives and the domain. We want to then look at critical value, determine if it's increasing or decreasing. That's going to give us our relative extrema. Point out any inflection points. Do the second derivative test, right, to give us that concavity. And then we want to sketch the graph. Okay. So as I mentioned in the beginning of class, Everything we do tonight is going to be building to put more details into our graphs. Okay? Questions? All right, so for this first problem, what we have is, so if you want to look at this, it's on page 290 of your textbook, number 4. And so what this problem is asking us to do is it wants us to identify the points of inflection. It wants us to identify the intervals where the function is concave up and or where it is concave down. Okay. So first, I am going to let's just sketch out over here. We want to know points of inflection. Okay. And so that's, remember, where we're shifting from one type to the next. So what I want to do is, let's get this highlighter. And I know I could see clearly that it's not dark enough. Clearly, somewhere around here, I know I am concave down, right? We can clearly see that. So I think that there's some sort of transition for this piece and this piece, right? So we can kind of see that somewhere right around right here, my graph is shifting from concave up to concave down, right? And so I would have inflection points. So my inflection points are going to occur at -1, 2, and at +1, 2. Okay. I will be concave down on the interval concave down. This is where I'm down right here. So that is from -1 to +1. We did that in blue. And then we are concave up on intervals that are from -infinity to -1, and from +1 to infinity. Okay, questions? You can see we're positive here. Right? So you could think of this as up, right? And then this one you could think of as down. Okay? Question. Okay? So this next question, number 12, this is asking us to give the coordinates of any critical points and classify each as a relative maximum or minimum or neither. Then we want to identify the intervals where the function is increasing or decreasing. We want to give the coordinates of any points of inflection. And we want to identify intervals where the function is concave up or concave down, and then sketch the graph. Okay, so it's starting to be a lot more But again, if we kind of follow the processes over here on how we sketch a graph, we're not going to miss some of those key things. And then also when we do like an exam, what I do is, and you probably saw, is I would put points of inflection, line, concave up, line, concave down, line. So it helps you to know all of the things that you need to report to me. I'm not going to just expect that you remember 7 different things, right? I'm going to list them out and help nudge you, and you just need to be able to remember how to do them. Okay? Question. All right. So now let's look at this. So the first one, we have our function. So let's do our derivatives, right? So g prime is going to be 10x minus 2, and g double prime is going to just be 10, right? So our first derivative, second derivative, that is going to help us out. Next, we want to do our critical values. Okay, so our critical points, remember we're setting first derivative equal to 0. I'll put that note here for you. To do that, so our first derivative equal to 0, so 10x minus 2 equals 0. So that gives me 10x equals 2, so x is equal to 1/5. This is my critical value. Okay, so we'll evaluate our original function at that, right? And so, and this will give us our y value. And then we'll also evaluate it at our second derivative, and that will give us our max or min. Okay, so this gives me 5 times 1/5 squared minus 2 times 1/5 minus 3, and that is a negative 16 over 5. Okay, so this gives me my y value. Okay, we do it at our second derivative. Well, 10, there are no x's, so it's just 10. Okay, so this is positive. So since it's positive, that means we have a minimum. Okay, and so we have that minimum at that point, 1/5 negative 16 fifths. 16 over 5. Okay. So now let's do our interval table. And our interval is negative infinity and 1/5 and 1/5 to positive infinity. Our test values are going to be 0, x equal to 0, and we could do x equal to 1. So our g prime, evaluate those at g prime. So g prime of 0 is going to equal negative 2. That is less than 0, so we are decreasing. Okay. Our derivative evaluated at 1, that's going to give me 8. 8 is greater than 0, so that is positive. So that shows that I have this maximum here, right? And so now we can look for our inflection point. So this was part B of the instructions. This was A for the critical values. B is that. C I don't know why this is starting, pen is starting to act up, sorry. So part C, our inflection point. Okay. And this is where we set our second derivative equal to 0. Okay. So 0 cannot be 10. So since there's no solution, there's no inflection point. Okay. Okay. Questions? All right. And part D was to graph this. So the second derivative is always positive. So the graph is going to be concave up over the entire interval from negative infinity to infinity. And so we can graph that out. Let's sketch out a table, x, g of x. So we can do -1, 0, 1/5, and 1. When we do that, we have 4, -3, -16/5, and 0. So we do know that we are decreasing and increasing. So when we plot these, they should fall in line with that. So we have 1, 2, 3, 1, 2, 3. And then this is 1, 2, 3, 4, 1, 2, 3, 4. Okay. So -1, 4, 0, -3, 1/5, a little more than -3, and then 1, 0. Okay. So this graph will look something like this, and we can erase these because we see that, yes, it did fall in line with what we expected. Okay. Question. Okay. So for this next type of problem, we're looking at problem number 34 on page 291. And for these, we just want to sketch the graph that possesses the characteristics that we're given here. Okay. So for the first one, it tells us that we are concave down at this point 1, 5. So let's plot 1, 5. Here's 1, here's 5. And it tells us that we're concave down. So I'm going to just put the little concave down sign there. So we'll plot out all these points and then connect the dots. The next one tells us that we're concave up at 7, 2. So we come out here 1, 2, 3, 4, 5, 6, 7, 2, about right here. And it tells us for this one that we are concave up. Okay. And the last thing, it tells us we have an inflection point at 4, 1. So we come over here 4, 1, and we have this inflection point. Okay. Actually, I put it at 7, 2. It's at 7, -2. I was like, that's not going to work. All right. So when we plot this, we know that we have to be coming from here, right? This is going to be our concave down. We're changing, shifting directions, and we go to concave up. And so our graph would look something like that, where this right here is my inflection. Okay, question. You'll see one of these in your homework for sure, and I believe you'll see one of these on the exam as well. Okay. The last example from this section, and then we'll take a 10-minute break, and then we will come back and finish the third section. But for this one, this is coughing velocity. So this is an application problem. And so it says that a person coughs when you have a foreign object in your windpipe, and the velocity of the cough depends on the size of object that is lodged. And suppose that a person has a windpipe with 20 millimeter radius. If a foreign object has a radius in millimeters, then the coughing velocity is given by this equation, which is what is needed to remove that foreign object. Okay. So it tells us that we're on this interval of 0 to 20. So if I have a radius of 0, that means I have no windpipe. Okay. If I have a radius of 20 millimeters, then that is the biggest that we can do for this this function equation. Okay. So what size of object requires the maximum coughing velocity to remove the object? Okay. So first we can do our derivatives. So our first derivative is going to be K is that constant, right? So K is some positive constant. So remember when we take derivatives, that can stay out there. But the derivative of 20r squared becomes 40r minus 3r squared. Okay. So our second derivative then would be K 40 minus 6r. Okay. And we can see that our first derivative exists for all r's from 0 to 20, right? So our interval is from 0 to 20 brackets because both the 0 and the 20 are included because of the equality that was given in the problem. Okay. And so we can determine a critical value because all of the numbers on the interval, our first derivative exists for all of the numbers on our interval. Okay? So if I take my first derivative, that is K times 40r minus 3r squared, set that equal to 0. I could divide both sides by K. That gives me 40r minus 3r squared equals 0. I can factor in r out of both of these. So that gives me r equals 40 minus 3r squared equals to 0. So what that means is r equals 0 or 40 minus 3r squared is equal to 0. Okay. If that is the case, then that is 40 equals 3r squared. So r squared is equal to, not r squared. This is just r because we pulled a r squared out. Or not a r squared, we pulled an r out. So this leaves me with r is equal to 40 over 3. Okay. Now let's do our second derivative test. Second derivative is equal to, well, we'll set that equal to 0. Evaluated at 0, that gives me K times 40 minus 6 times 0. So that gives me 40. Remember that K is some constant, some positive constant. So 40K is going to be greater because K is a positive constant, right? So my second derivative then evaluated at 0 is that. My second derivative evaluated at 40 over 3 is going to give me k times 40 minus 6 times 40 over 3. And that equals negative 40k, which is less than 0, right? Because a negative times a positive is still a negative. So since our second derivative is less than 0, we know that there is a relative max. And that occurs at x equal to 40 over 3. Okay, so for the object whose radius is 40 over 3 millimeters, the maximum velocity is needed to remove that object. Okay, question. All right, so it is 8:13. So let's round that to 8:15 and take a 10-minute break. So we'll come back at 8:25 p.m. and we'll finish out tonight's lecture with section 3.3. All right, it is 8:25, so let's go ahead and finish our lecture with section 3. So in this section, we will continue sketching graphs. We will determine, now we're going to determine asymptotes of functions as well as graphing rational functions. And we'll also find limits involving infinity in this section. Okay. So a few definitions first. A rational function is a function that we can describe where we take one polynomial divided by another polynomial where the polynomial in the denominator cannot equal 0, right? That would make our graph or the function itself undefined. We also will look at vertical asymptotes. If you remember back from algebra days, a vertical asymptote really is where our denominator is equal to 0, what makes that function undefined. When we look at it in terms of calculus, we can look at that as when we're looking at it in terms of limits. So if the limit is as x approaches a from the left, if our limit is either negative infinity or positive infinity, we'll have a vertical asymptote. Similarly, if x is approaching a from the right and we have positive infinity or negative infinity, we will also have that vertical asymptote. And so I put the graphical representation of that down here for you. So things to keep in mind, the graph of a rational function never ever crosses a vertical asymptote. If the expression that defines that radical or rational function is simplified, it means that when you simplify it, it means that there's no common factors other than 1 or negative 1. Then we can say that there's a vertical asymptote, okay? If you think back to this section in Math 161, a vertical asymptote occurs, as I mentioned, whenever our denominator is equal to 0, okay? Any questions so far? Okay, so we'll have a horizontal asymptote, all right, when the graph of a rational function it may or may not cross a horizontal asymptote, right? Horizontal asymptotes occur when the numerator is less than or equal to the degree of the denominator. Remember, the degree of a polynomial in one variable is the highest power of that variable. Okay, and so we can determine our horizontal asymptotes if we look at our limit as it approaches or as x approaches negative infinity, if we're at some value, or if x approaches infinity and we get a certain value. And so I've included those graphical representations here as well. So if you look at the limit, the first one, you can see the limit is getting really close to that y equals b line there. But in the third one, you can see that we've actually crossed the line. It isn't as restrictive as an asymptote, as a vertical asymptote, where you cannot cross the line. Okay. And then finally, we'll have what's called a slant asymptote, or you might see it as an oblique asymptote. And we probably won't really deal with many of those in this class, but that occurs when the degree of the numerator is exactly 1 more than the degree of the denominator. Okay. All right. So what I've given you here is just another look at all of the asymptotes. You can get this off of page 298 in your textbook. So it's really all the things that I've already said, but I wanted to put it here in your notes that you can download from this PDF at the end of class. Okay. And then also adding to the strategies from last section, we now will learn, we're going to add our X and Y intercepts. We're going to add our asymptotes, and then the rest of this is the same as what we were doing in the last section, right? So as I mentioned earlier this evening, everything we do today is going to continue to build so that we can start getting more and more elaborate graphs based on some of these functions, okay? Any questions so far? All right, so the first couple of examples, we're going to look at determining vertical asymptotes, okay? So this comes from page 305 in your textbook, number 6. And remember, when we want to determine what our vertical asymptote is, we first want to write our function in simplest form, okay? So when we write our function here in simplest form, that is x plus 2 over, we can factor an x out of all of those terms. So that's going to leave me with x squared minus 6x plus 8. And now I can actually factor that as well. So this gives me x plus 2 over x. And then we need to factor this. Again, if you have trouble with factoring, make sure that you visit Khan Academy, refresh your Math 161 notes, or let me know if you need help finding some additional resources for factoring, and I will be happy to do that. So x minus 4 and x minus 2. So what that means is our denominator cannot equal 0, right? So the denominator cannot equal 0. So that means that happens when x equals 0, or x minus 4 equals 0, or x minus 2 equals 0. Okay, so that would be x equal 4 here. If I added 4 to both sides, add 2 to both sides over here, and that gives me x equal to 2. Okay, so I will have vertical asymptotes at x equals 0, x equals 2, and x equals 4. Okay, question. Okay, so for this next problem, again, let's simplify. This is x plus 6 over, when I factor this, I get x plus 6, x plus 1. Notice I have the same term in the numerator and the denominator, so I can cancel those out and simplify this to 1 over x plus 1. Okay, so I still, x cannot equal 6 because it will make my denominator equal to 0. But unlike a vertical asymptote, this would be, I would say at x equals 6, there is a hole in the graph versus a vertical asymptote. So my vertical asymptote is only going to occur when x is equal to -1. So if I looked at this and if I had a graph, right? So here's 1, 2, 3, 4, 5, 6, and -1. Let's just say that I had a point here, or at -1, I'm going to have this vertical asymptote here. I'm not going to have a vertical asymptote at 6. Rather, wherever the graph is, I might just have a hole. So this graph could look something like this, right? So instead of having that vertical asymptote here, I just have a hole in the graph where my graph cannot equal that value 6. This right here is a hole. Okay? Questions? Okay, so now let's look at some examples with the horizontal asymptote. So for this one, um, in college algebra or in the pre-calc one, we had some rules about the number, the degree of the exponent, the degree of the numerator and denominator, and that sort of stuff. In calculus, what we do is we find the limit. Okay, so we find the limit as x approaches infinity, and then similarly as x approaches negative infinity. So this is 3x squared over 6x squared plus x. So when we do that, remember from chapter 1, we need to do the largest exponent of the denominator. So this is the limit as x approaches infinity of 3x squared. My largest denominator is exponent is x squared. So we're going to divide all terms by this x squared. Okay. And simplify that down. So that gives me the limit as x approaches infinity of 3 over 6 plus 1 over x. Now when we substitute infinity into here, it's going to drive this here down to 0, right? 1 over a really, really, really large number is very close to 0. So this is going to be 3 over 6 plus 0. So 3 over 6, which is 1/2. Okay. Similarly, we have to do the limit as x approaches negative infinity. We can go to that simplified version already, and we're getting this is going to be 3 over 6 plus 1 over x. When you plug in the negative infinity, that's still going to drive down to 0. And so this will be 3 over 6, which is 1/2. So we have a horizontal asymptote at the line y equals 1/2. Okay. Questions? Okay. So in this one, we're going to do the same thing. And so when we look at this, this is equal to the limit as x, well, not equal, we'll just say the limit as x approaches infinity of 8x to the 4 minus 5x squared over 2x cubed plus x squared. So again, the largest exponent in my denominator is this x cubed. So we take the limit as x approaches infinity of 8x to the 4 over x cubed minus 5x squared over x cubed, 2x cubed over x cubed plus x squared over x cubed. Okay. And all of that is going to simplify down to, we have our limit as x approaches infinity. This is going to be 8x, right? Because I have 3 in the denominator, 1 in the numerator. Minus, this is going to go to 0. This one will also go to 0. And the first term over there, so this is going to be 8x minus 0 divided by these cancel, so 2 plus 0. So that simplifies my limit as x approaches infinity of 8x over 2. So that would, we could simplify that as just 4x, right? So we plug in that infinity and we actually get 4x, and that equals 4 times infinity. So that is infinity. And therefore, because it's not a specific value, we know that there is no horizontal asymptote. Okay. You could do the same process for negative infinity, and you'll see that you would get the solution is negative infinity. If there's no horizontal asymptote as it approaches infinity, then there's not one for negative infinity either. Okay? Question.
Professor,
Yes.
I don't understand. I'm trying to understand how did you get from 8x to the fourth minus 5x to the second, square to 0. That's what I'm getting confused.
This is if I have 5, forget the 5, right? So I have an x squared over an x cubed. That simplifies to 1 over x. So we have this 5 here, right? So it would be 5 over x. If I have 5 over 10,000, that's really going to be close to 0.
Oh, okay.
Do you remember back from chapter 1 when we take a derivative, right? And or the limit of something, and it gets really, 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 really close to 0. I'll never actually reach 0, but if I put a large enough value of x in there, if I put 5 divided by 1,000,000, I mean, there's so many zeros I can't even distinguish between it and 0. And so that's why we can say that that number would go to 0. So it becomes kind of a non-player in the equation.
Okay, thank you.
Uh-huh. Any other questions? And so like these ones right here, they just canceled out with each other because it was an x cubed over an x cubed. So it just left me with 2 because they canceled with each other. Whereas this one, I have the x squared over an x cubed. So it leaves me with an x when I simplify it. It leaves me with an x in the denominator. When I plug infinity into that, or any large value for that matter, it'll drive it really close to 0. Okay. So the next thing that we have here, and I think that this is the only problem, but it's going to take us a couple of pages to get through, right? Because we're going to go through all of those steps to graph this. So ultimately, at the end of this problem, we'll have a graph of this without actually using our calculator to show us what that graph looked like. Okay, so it's probably going to take us a little bit of time to get through it, but we're going to do it in a very systematic order, kind of following along with these steps here, where we'll look at the intercepts, and then we'll look at the asymptotes, and then the derivatives, the domain, the critical values. Where is it increasing, decreasing? What are my inflection points? Where am I concave? And then we'll get to the graph. Okay. All right. So first of all, if we look at this, let's simplify it. So simplifying it gives me x plus 1 over x minus 3, x plus 1. Okay, that simplifies further to 1 over x minus 3. Okay, because we have an x plus 1 in the numerator and an x plus 1 in the denominator. Okay, all right, so when we look at this, then we have domain restrictions. And it's restricted at x equal to -1 and x equal to 3, right? So we do know that we'll get to it in our vertical asymptotes. So the restriction, the vertical asymptote is going to be at the -1, and the whole is going to be at 3. Okay. And we'll discuss that further though when we do the asymptotes. So the first thing that is on our list, right, is intercept. Okay. So the intercepts, we can calculate those. First of all, f of x equal to 0 has no solution. Since it has no solution, then that means that we are not going to have an x-intercept. Okay. So, but we do need to also look at f of 0 for our function. And so that's going to be 0 plus 1, 0 squared minus 2 times 0 minus 3. And that is going to simplify as a -1/3. So we have a y-intercept at the point 0, -1/3. So that's going to be important to keep track of. That's going to be one point that we plot on our graph at the end. Okay. So I can highlight that now, just so that we keep track of it. Okay. All right. Next thing we want to look at. Okay. The next thing we want to look at is our asymptotes. Okay. So our vertical asymptote, remember, the denominator is 0 for x equals -1 or x equal to 3. And since x equal to -1 also made the numerator equal to 0, we have to look at the limit to determine if it's a vertical asymptote or if at that point, if there's a vertical asymptote, right? So if we look at the limit as x approaches -1, right? We get x plus 1 over x squared minus 2x minus 3 equals the limit as x approaches -1 of 1 over x minus 3. And that equals 1 over -1 minus 3, so -1/4. Since the limit exists, okay, the line x minus 1 is not a vertical asymptote. Okay, so since the limit exists, the line x equal -1 is not a vertical asymptote. Instead, we have a removal, we have the hole there at that point. We have a hole at that point, -1, -1/4. And so we'll want to make sure and track that on our graph as well. Okay. And that'll be signified on the graph as I showed you in that example a little earlier, just as a hollow dot on the graph. Okay. And the denominator is 0 at x equal to 3, and the numerator, so we would have a vertical asymptote at x equal to 3, right? So that also we will want to make sure and include on our graph. Okay? Now so this was where we were looking at vertical. Okay? Now let's look at horizontal. So the degree of the numerator is less than the degree of the denominator. Is less than okay. So that tells us y equals 0 is a horizontal asymptote. And if you have a horizontal asymptote, you cannot have a slant asymptote, slant or oblique. So we don't have to check that one. Okay. All right. Question. The third thing is derivative and domain. Okay. So our first derivative I'm going to write it over here, and it seems like that corner is. So our first derivative is the negative x minus 3 to the negative 2. That is a negative 1 over x minus 3 squared. Let's move that over here. That's our first derivative. Our second derivative is going to be 2x minus 3 to the negative 3, or 2 divided by x minus 3 cubed. And the domain then is going to be, we have that vertical asymptote restriction, so our domain, I don't really know why this is so blurry, is negative infinity to our vertical asymptote, and then from our vertical asymptote to infinity, okay, as determined in step 2. Okay? Question. All right, number 4 is critical points. I'll move this up to the top in a minute. The top corner is a little wonky to write on. Okay, so we're looking at our critical point. Remember, if our derivative exists for all values of x, in this case, it does, except for all values of x except for 3, but 3 is not in our domain. So we can say that that 3 is not a critical value, right? Because it's not in our domain. Then the equation f prime of x has no solution. So there are no critical values. Okay, so I'll kind of write that out here. So f prime of x exists for all values of x except 3. Okay, but 3 is not in our domain. So x equal to 3 is not a critical value. Okay, so we have no critical values. So now we need to move on and determine where we're increasing, decreasing. So we want increasing, decreasing, extrema. Okay. So we'll look at our intervals. Where did our graph equal to 0? So we have infinity to -1. We had -1 to 3. And we have 3 to infinity. Okay. So we have to have a test value in each of those. We want to determine our sign of our derivative and then what is that result for each of those. So for this first one, we can use x equal to -2. Here we can use x is equal to 0. And here we can choose our test value x equal to 4. So when we plug that in, we end up with this is less than 0. This one is less than 0, and this is less than 0. So they are all decreasing. Since they are all three, since there's no critical point, there's no relative extrema. Okay, since no critical value, there is no relative extrema. And so you can see that because they're all three decreasing. Okay, questions? This next thing is we're looking for our inflection points. So you're looking at the second derivative here, okay? And it does not, so the second derivative does not exist at 3. Because 3 is not in the domain of the function, therefore you can't have an inflection point, okay? So we have no inflection point. Okay? Question. Okay, so the next thing is to look at concave. Okay, and so remember this one is looking at same intervals, but now we're looking at our second derivative test. And instead of result, we're talking about is it concave up or is it concave down? So we have our interval. And it is negative infinity to -1, -1 to 3, and 3 to infinity. Test value, we can use the same test values, x equal to -2, x equal to 0, x equal to 4. Our second derivative, then, this one is going to give me, I end up with -2/125, so that's less than 0. This one ends up being -2, so that is less than 0. And this one, my second derivative evaluated at 4 gives me 2, which is greater than 0. So when I try to look at my concave, so I'm going to be concave down for the first two where they're less than 0, and then I'll be concave up for the one that is greater than 0. Okay? And now we can take all of this information to help inform the graph of this function. Okay. I'm going to put some graphing paper on here. Okay. So the first thing we want to do is the eighth thing is graph, right? So let's build a little bit of a table to help us with that. Okay, and our function f of x, remember, is really 1/x minus 3. So some of the points, remember from 1 and 2, steps 1 and 2, we highlighted some things. We highlighted the whole. That took place at -1 and then -1/4. This was the whole out of step 2. And then we also had our intercept at 0 and -1/3. This was our y-intercept out of step 1. And then we also had down here a little ways, we had 3, we had a vertical asymptote, and that came out of step 2. Okay. So now let's fill in some of the things on the sides above and around this, right? So we can look at the value -2. When we plug that into our equation, we get a -1/5. Let's plug in a 1 and a 2 in here just to see what the graph looks like. So when I plug 1 in there, I get 1/1 minus 3, so that is a -1/2. When I plug a 2 in there, I get a value of -1. And let's do a couple of slot points on the other side of that asymptote to help get the shape of that graph. And when I plug a 4 in there, I'll get a 1. And when I plug 5, I get 1/2. Okay. So now we have some points that we can plot. Okay. So I'm just going to plot them in here. So I have -2 and 1/5. I have a point about right here. I have another point, -1, -1/4. That's where I have this hole. So that's a hollow dot. I'm going to just highlight that there in orange. Have this point 0, 1/3. Okay. I have 1, -1/2. I know this is not quite, oops. If this is 1/2, this is more like 1/3. Okay. And what else do we have? We have 2, -1. Here's 2, here's -1. I have at 3, I have this asymptote. Okay. And at 4, I am at 1. And at 5, I am at 1/2. Okay. So this graph then, oh, and you remember we also had that horizontal asymptote at y equal to 0. Okay. So this one, we're going to get really, really close and then have to skip open and then keep coming, right? And for this one, I will get really close to that horizontal asymptote and then shoot up. Okay. And so that is a rough sketch. So if you put that function into from 3 pages ago into your calculator, you would get a graph that looks something similar to this. Okay. Questions? All right. That is all of the material I have for you this evening. Don't forget, we do not have lecture next class period. Next Monday, you will have your second exam. You will take that in Canvas using the lockdown browser, choosing the 100-minute window in the day that works best in your schedule. Don't forget to show your work. If you don't show your work, then you will not receive credit. And make sure your work is legible in chronological order and in one document saved with your last name as the file name first. Okay. So it'd be last name, comma, first name, and then the rest. And you can see how that needs to be named based on the upload instruction. Okay. All right. Any questions? All right. If you guys don't have any questions, that's all the material I have for you this evening. And I will see you all back here 2 weeks from tonight.